Black holes are the universe's most enigmatic entities. Their voracious nature lets them devour anything close enough, growing in size with each feast. But what's the range of their sizes? Dive in with me. To give birth to a black hole, you need immense gravitational collapse. Typically, this collapse results from massive stars exhausting their life. Imagine condensing the sun to a mere 1.8-mile diameter, or compressing Earth to pea size. What results? An incredibly dense object with immense gravitational pull, a black hole. While we commonly think of colossal black holes, tiny ones might exist. Known theoretically as primordial black holes, they could be minuscule, down to atomic dimensions. These ancient entities might predate even atoms, originating just post the Big Bang. Back then, with the universe in a tumultuous state, even a slightly denser particle might have become a black hole. These atom-sized black holes might weigh as much as mountains, while those weighing like Earth might only be coin-sized. Though fascinating, their lifespan would be brief due to extreme temperatures making them evaporate swiftly. Our universe houses the known category, stellar black holes. Their mass is often multiple times that of the Sun. For context, the Sun's weight is a mind-boggling number with 30 zeros. The smallest recognized black hole is 2, 4 times the Sun's weight. It drifts through space, hunting for cosmic prey. Gaia BH1 is our nearest neighbor, with 10 times the Sun's mass. At a staggering distance, M33X7, some 3 million light-years away, currently consumes a blue giant far bigger than the Sun. Transitioning to larger ones, we find intermediate mass black holes. They achieve their size by either consuming numerous stars or frequently merging with other black holes. A prominent example weighed 142 solar masses, overshadowing some earthly regions. A pair was recently spotted in a galaxy 17 billion light-years away. Though they'll eventually merge, their current interaction unleashes enormous energy. But the true behemoths in this category are the supermassive black holes. These cosmic giants have masses millions or even billions of times greater than the Sun. The colossal nature of supermassive black holes is baffling. How did they grow so immense in a universe that's only 14 billion years old? Enter quasi-stars, hypothetical stellar titans that dwarf even the largest known stars, like Stephenson 2.18. These could have birthed from the universe's early days, with cores collapsing into black holes even before fully forming. Inside a quasi-star, its newborn black hole would feed on the star's matter, growing larger while maintaining the star's equilibrium. Over millions of years, the black hole would swell, resulting in the supermassive black holes often found at galaxy centers. Contrary to belief, galaxies don't orbit these giants. For instance, our Milky Way's heart houses Sagittarius A, a 4 million solar mass black hole, just 17 times the Sun's size. However, not all black holes are dormant. The one in BL Lacertae gobbles up vast quantities of gas and dust. Then there's the black hole in Messier 87, captured in humanity's first black hole image, capable of swallowing our solar system up to the Orion Belt. But the universe harbors even grander entities, ultramassive black holes. These monsters outshine thousands of galaxies, drawing in everything in their vicinity. OJ 287's center features one weighing 18 billion solar masses, so vast another black hole orbits it. Lastly, meet TON 618, the universe's largest known object, with a mass surpassing 66 billion suns. Its brightness exceeds 100 trillion stars, illuminating even from 18 billion light-years away. The enigma? We're observing TON 618 from 10 billion years ago. Its current size remains an awe-inspiring mystery, likely magnitudes larger than our last glimpse.
Black holes are like omnivores. They'll eat anything in their way if it gets close enough, including planets, stars, clouds of gas, or some very unfortunate intergalactic travelers. Not that it really gets hungry and goes after space objects, it simply swallows whatever comes nearby. It stretches giant space bodies until they're thin, like spaghetti, and rips them apart atom by atom. A black hole is a huge amount of matter that comes in a very small package. It's like you squeeze a star 10 times bigger and more massive than the sun into a small area with the diameter of New York City. You get an extremely massive, compact, and dense pit with gravity so strong, not even light can escape, not even another black hole. They don't have a fixed point in space. Stars, planets, asteroids, comets, black holes, and everything in the universe is in constant motion. That's why things get so chaotic from time to time. Researchers found a giant black hole at the heart of one galaxy being eaten by an even bigger one. A black hole can get extremely big. At the centers of most giant galaxies are black holes that can grow millions to billions of times the mass of our sun. One of the ways to become so big is by eating others of its kind. A black hole merging with another black hole is one of the most energetic and powerful things in the universe. Picture this: 1.3 billion years ago, two black holes are circling around each other. The bigger one pulls the smaller black hole inwards, and now they're locked together in a spiral. Through time, that orbit starts decaying, but very, very slowly. These two black holes are constantly getting closer and closer. As they approach one another, the disks of orbiting dust and gases that surround them mix and create an intense towering vortex. It extends and goes pretty high above the center of that disk. At some point, they finally merge into one extra big, supermassive black hole. As they're merging, they kick out gravitational waves. These waves tell us a lot about black holes, but they can't reveal their precise position. So, scientists need some electromagnetic signal that will find the black hole's location, like radio waves, X-rays, or a flash of light. We can't see black holes, but we can detect their effect on space objects that are surrounding them. When a black hole passes through a cloud of matter, its strong gravity will pull matter inward. If a star or a planet comes close enough, the same will happen. The attracted matter then accelerates, which means starts to move very quickly and heats up. The black hole then starts emitting X-rays that radiate in the area surrounding it. The energy of X-rays affects the neighborhood and can, for example, spur the growth of new stars. And finally, bam! They collide. It's a massive burst of energy, one of the biggest bangs ever since the Big Bang. In less than a second, that collision emitted more energy than all of the stars in the visible universe together at the same time. Black holes can become huge, but not necessarily. Stellar mass black holes have a mass similar to the Sun, and they can be very small. The one scientists found in 2019 is located 10,000 light years away from us and is only 12 miles across. They really have a reputation for destruction, but black holes are just another source of gravitational force, similar to stars. That means it's possible for a space body to orbit them, if it moves fast enough, of course. Let's say there's a black hole with the same mass as the Sun. The speed a space body would have to move at is the same as the one needed to orbit our Sun, if the distance is the same. That's a theory. In reality, planets don't really orbit black holes, because those that have a mass similar to our parent star are mostly the remnants of giant stars that ran out of nuclear fuel and eventually exploded. That's how black holes are created in the first place. And chances are that none of those planets nearby will survive it. But 30 years ago, scientists discovered the first planets beyond our solar system. These planets were found orbiting a pulsar, which is also some sort of supernova remnant. We don't know how they survived the explosion of their parent star. It's possible they may have been created after the destruction from debris that formed after the explosion. Scientists even have a theory that black holes are possibly wormholes, something like tunnels to other galaxies. That means they don't destroy objects they swallow, but send them somewhere. The theory says the object that enters and then goes out on the other side leaves the tunnel through something opposite of the black hole, a white hole. It probably looks similar to its companion, with all that spinning and similar mass. There could be a ring of gas and dust around the event horizon. The event horizon is the point of no return, the part of a black hole where nothing escapes. Unlike a black hole, a white hole lets light and all the matter leave, but none of that will be able to enter the portal once again. About 50 years ago, Stephen Hawking realized that black holes leak energy. Scientists then developed the theory that a white hole could be born out of a black hole. They're still not sure how the black hole disappears, but in this scenario, it would grow so small it no longer can have such strong gravity that makes it swallow other objects. So, it might turn into a white hole then. Such a hole would be similar in mass to something really light, like human hair. It wouldn't be so dramatic as its black hole ancestor, but it would still hide mysteries in its interior, the information of all space objects it had swallowed previously. It would eventually spit out that information and get so big, it would dominate the universe. White hole behavior, opposite of black holes and all that sucking the matter inward, could be compared to the Big Bang explosion, where the universe is expanding and new objects are forming. But even if something like this happens, it may only be possible trillions of years from now. And there's an issue. Even if some big white holes did form somewhere in space, they probably wouldn't last too long. Outgoing objects would collide with the matter in orbit, so the whole system would collapse and turn into a black hole once again, since they're also formed after supernova explosions. Stars, asteroids, comets, galaxies, and planets, all those space things we can see, make up nearly 5% of the universe. About 25% could be dark matter, a mysterious substance we can't actually see, but assume it's there because everything in the universe moves to its gravitational tune. This dark matter is kind of like a spider's web. It holds all those galaxies that move pretty fast together. Its evil twin is called antimatter. Antimatter particles are like the opposite version of the matter, the same mass but opposite electric charge. When they collide, antimatter wipes out the regular matter, and the result is pure energy. Dark matter probably makes the universe expand even faster than it used to do. One of the latest theories says it could be responsible for the huge asteroid strike that made the dinosaurs go extinct, too. The universe doesn't have a center, but galaxies do. The Earth makes a circle around the center of the Milky Way once every 250 million years. This orbit is not straightforward, but we can roughly predict it. Once in every 60 million years, we go through the crowded region of our galaxy, known as the galactic disk. At the same time, we can track some harsh mass extinctions in the history of our planet, including the asteroid that wiped out the dinosaurs about 66 million years ago. Professor Rampino from New York University proposes that dark matter has a gravity that could throw nearby space bodies into the Earth's path whenever we enter the galactic disk. That means some asteroids and comets that would usually be far away from us are flung towards our planet. The biggest thing in the universe, at least the one we know about, is the Hercules Corona Borealis Great Wall. It's a cluster of galaxies 10 billion light-years across, bound together by gravitational force. The biggest elliptical galaxy is IC 1101 and has a diameter of 4 million light-years. The smallest galaxy, Segway 2, we've discovered so far, has a diameter of a little bit over 220 light-years. It's pretty faint and has only 1,000 stars. For comparison, our galaxy has 100,000 million stars. It orbits the Milky Way. We fly away from Earth to look at it from a distance. It glows like a holiday tree. Big cities look like yellow spots at night, and during the day, we see strange structures, like a palm tree-shaped island in the UAE, or a dark band that runs all the way through China, the Great Wall. These are traces of human existence. Now let's point our telescope at other planets. Mars, it's just an empty, endless desert. Venus, only rocks and volcanoes. Even if we look into distant space, all the planets out there are deserted and lifeless. Not a single trace of an extraterrestrial civilization. Many people are convinced that life on Earth isn't unique at all. Here's our galaxy. There are billions of sun-like stars. And here is the entire observable universe with billions of such galaxies. There's an almost infinite number of stars, and near each of them, there may be habitable worlds. But we may not have found life on other planets because it hides from us under the surface. For example, there's Europa, a satellite of Jupiter, slightly smaller than our moon. Its structure resembles a soft-boiled egg. Its surface is a hard crust of ice, but if you take a big enough drill, you can get to the liquid yolk, an ocean of water. Jupiter and its satellites are very far from the sun, so it's quite cold there, about 270 degrees below zero. So liquid water instantly turns to ice. But Jupiter has a strong gravitational force that causes a lot of friction inside Europa, and its core heats up. The heat melts the ice, and we have a watery ocean under the surface. Water is the foundation of all life, so there could be simple bacteria in that ocean. And who knows, maybe there are other life forms out there. For example, weirdly shaped fish. Because of the weak gravity, their bodies are built differently, or something like whales feeding on plankton. In 2009, scientists found a planet that is completely covered by an ocean, GJ 1214. It's about 40 light-years from Earth, and about 75% of its mass is water. Still, the temperatures on this planet are so high that water evaporates and takes the form of super liquid water. There's so much steam that it feels as thick as water itself. No life could exist in such conditions. But scientists have recently found at least 24 planets better than Earth and called them superhabitable. These planets orbit distant stars in their habitable zone. It's the sweet spot at a perfect distance from the star. In our solar system, Venus, Earth, and Mars are in this zone. A superhabitable planet must be 10% larger than Earth and have stronger gravity. That way, it can have a denser atmosphere. A temperature 8 degrees higher than on Earth would make the planet more humid. This would encourage a variety of living organisms there. These planets may be great for life, but it's hard to tell if there is life there already. The main marker that would confirm the existence of an advanced civilization there might be radio waves. Imagine a habitable planet similar to Earth. In the process of evolution, intelligent beings appeared there, like humans. They're much taller because of low gravity, and their eyes are adapted to the light from another star, much brighter than the sun. Sooner or later, this civilization will have to use radio waves to communicate with each other. We can think of these waves as loud sound from speakers. Here's Earth. We're now actively using radio waves, and the noise coming from our planet is pretty serious. If a neighboring planet had radio telescopes, big dishes that catch these waves, they would realize that life is blooming here. There are many radio telescopes on Earth that are pointed into distant space, waiting for a signal from aliens. But we haven't received anything yet. Still, that doesn't mean there isn't a planet somewhere in the universe that emits radio waves. It's all about distance. We're jumping 200 light-years to another star. Suppose there's a planet X where life exists. The civilization here is advanced enough to use radio waves, so they release the first wave into space. Our radio telescopes won't be able to pick it up until 200 years later. This also works the other way around. Radio communication on Earth has only existed since 1895. Our radio signal won't reach Planet X until 2095, and only then the aliens will hear our voice. But this radio noise doesn't stay for long. Every year, our technology improves, and our radio noise decreases. We're beginning to use mobile communication, cable TV, and fiber optics. This all reduces the volume of our planet in the radio spectrum, and soon it will simply become invisible to other planets. The same thing is happening on the other side. So, the radio waves coming from civilizations are a brief blip on the cosmic scale, and we can't accept radio silence as proof that extraterrestrial life doesn't exist. A giant telescope, which could take a direct photo of a possibly inhabited planet, would change the situation. We zoom in on the photo, and there it is! We see alien cities with tall buildings and lots of antennas. But now, we can't look that far away. We can take pictures of Mars and its satellites, and even their quality misleads us. For example, Cydonia. It looks just like a human face on Mars. We thought there used to be an ancient civilization there that made some sort of sculpture or memorial. More extravagant theories said it was the remains of a giant human, and there's a whole body of it under the sands of Mars. But in fact, it was just a hill. Strong winds blew out some hollows there, and when there was a shadow in those hollows, we took them for human eyes and a mouth. Or a monolith on Mars' satellite Phobos. We found a smooth rock there that was almost as tall as the pyramid of Cheops. The news has spawned many theories about the civilization that built it, but it turned out to be no more than a rock. The infinite number of stars and worlds around them almost guarantees the existence of other civilizations, so why wouldn't they come to Earth, right? We think that life throughout the universe develops in similar scenarios. The emergence of simple life forms, followed by evolution and growth of a technologically advanced civilization. But, just like on Earth, cataclysms happen there too, causing mass extinctions. Meteorites, for example. Perhaps there was a civilization out there ready to go into outer space, but a huge meteorite, like the one that wiped the dinosaurs off the Earth's surface, made that civilization disappear, and life on that planet began a new cycle from scratch. In addition, the more advanced the civilization, the greater the risk of its self-destruction. Scientists might conduct experiments in machines like the Large Hadron Collider and accidentally create a black hole there. It would begin to swallow everything around it and grow in size. Soon, all the super-developed cities of this civilization and the entire planet would simply disappear. Another possibility for super-advanced civilizations is to travel through wormholes. Those are tunnels in space-time between universes. Aliens might travel through them and lose interest in going back. But it's also possible that life on Earth is unique. That's because our planet was formed thanks to a number of incredible coincidences. The first is the location of our solar system in the galaxy. In the Milky Way, there are constant fireworks of exploding supernovae. The radiation from these explosions destroys everything around it at great distances. Our solar system is right in the sweet spot of the galactic orbit where we're safe from such explosions. Another factor is the moon. One theory of the formation of the moon says that about 4.5 billion years ago, a meteorite the size of Mars crashed into us. If the impact had been straight, the Earth would have just broken apart. And if that meteorite had only scratched the Earth, the pieces would have just flown away. But the collision occurred precisely so that part of the meteorite remained in Earth's orbit and formed the moon. Then, the moon stabilized the Earth's rotation and heated our core with gravity. Only then, our planet developed a magnetic field, which protects us from the solar wind. Other scientists believe that life outside Earth may be biochemically different. Carbon and water are the basis of our bodies, but carbon could be replaced with silicon or phosphorus, and water could be replaced with ammonia or methane. These atoms could form molecules of different shapes and perhaps assemble into a living organism. Life based on such elements would be unlike anything seen on Earth.